So now we're going to sketch something that's a little bit more difficult, and we're going to sketch the region in the complex plane that's given by this equation here, z minus I equals 2, or the modulus of z minus I equals 2. So what's sort of tricky about this one is it's hard to interpret immediately what this term actually means. What does the modulus of z minus I actually mean? Okay, so if you think about a general situation where you've got z minus z naught rather than z minus I, it turns out that if you take the modulus of z minus z naught, it just equals the distance between z and z naught in the complex plane. Now, what happens if you look on this diagram, so here's my point z naught, here's my point z, and I've just let z naught be equal to x naught plus I y naught, and I've let z be equal to x plus iy. So I've drawn those coordinates on the picture here. So z naught has real part x naught and imaginary part y naught, and z has real part x, imaginary part y. So then if I form this right-angled triangle, then this distance, this side, the length of that side is just x minus x naught, and the length of that side is y minus y naught. So that means the length of the hypotenuse is just the square root of x minus x naught squared plus y minus y naught squared. And if you think about what's going on here with the modulus of z minus z naught, that's just equal to x plus iy minus x naught plus I y naught, which is x minus x naught plus I times y minus y naught. And if you work out the modulus, that's just square root of x minus x naught squared plus y minus y naught squared. And so the expressions are just the same. So this z minus z naught modulus represents the distance from z to z naught. Okay, so then when we're looking at this particular example, this says we're looking at all complex numbers z whose distance from this point, z naught, in this case it's I, so that was my z, that's my z naught. We're saying that we're looking for all complex numbers whose distance from I is equal to 2. So that's how we're interpreting that statement. Okay, so let's draw a picture and see what we've got here. So I'll see if I can draw some straight lines this time. That's a bit better, isn't it? So that's the real axis, and this is the imaginary axis. And remember, we're looking at z minus I equals 2. So this is our fixed point, z naught. So we're going to draw that point here, that's the point I, on the imaginary axis, and we're looking at all complex numbers z whose distance from I is equal to 2. So let me change my colour for a minute. So, all right, let's think about just thinking about a couple of points that satisfy that equation. So if I go down here to minus I, then the distance from I to minus I is equal to 2, so that point's going to be included. If I go directly across there, a distance of 2, then that point is going to be 2 along the real axis, and it's up I in the imaginary axis, so that point's going to be 2 plus I. If I go in the negative direction, I can go out minus 2, and that point's going to be minus 2 plus I. If I go 2 straight up, I'm going to get to the point 3I. And there are going to be a whole bunch of other points. If I go out from all directions from that point I, a distance of 2, I'm going to get infinitely many points. And if I join them all up, and this is going to be impossible to do on this screen, if I join them all up, what I'm going to get is something that looks like a circle, but actually is a circle. So when I sketch this equation, taking into account all possible complex numbers z whose distance from I is equal to 2, then I get a circle, centre I and radius 2. Okay, so in general, if I have something that looks like this, z minus z naught equals c, and I try and sketch that in the complex plane, then it will be a circle of centre z naught and radius c. If it was given it in this form, z plus z naught equals c, then that's easy. You could just write that as z minus z naught equals c. So this would be the centre. This would be the centre. And the radius would still be c. Okay, so that allows you to draw a whole class of examples if they're given to you in this form. So just staying with this example for a minute, so I've still got z minus I equals 2. If we write this in Cartesian form, then you'll see why this gives you a circle. So what we're going to do is we're going to, instead of just having z minus I, we're going to let z be equal to x plus iy. So this is just an arbitrary complex number written in Cartesian form, and I'm going to substitute that into my equation. So what I've got is x plus iy minus I equals 2. And then I'm going to collect the real and imaginary parts together. So this is x plus y minus 1 times I, modulus of that equals 2. And I'm going to take the modulus here. So I'm actually going to work out what it is. So remember that the modulus of a plus ib is just the square root of a squared plus b squared. So what we have here is the square root of x squared plus y minus 1 squared equals 2. So I'm just taking the modulus of that side, and now I'm going to square both sides. So I get x squared plus y minus 1 squared equals 2 squared. And so when we write this expression in Cartesian form, you can see exactly why it gives you a circle. So if you think about our work on circles earlier in the semester, this is exactly the equation of a circle. It has centre 0, 1 and radius 2. And if you drew that in the xy plane, then it would have centre 0, 1, centre 0, 1, and it would have radius 2. So it would look exactly like the picture that we just drew in the complex plane, except now we're just representing it by a pair of real coordinates. Okay, so that gives you a little heads up actually. If you look at the examples following this one, if you look at the examples and you see something that you're not quite sure how to sketch because it's written in terms of a complex number z, then just replace the z by x plus iy and rearrange your equation and see if you get a better idea of what's going on. So there's some examples that you can try at home, and then if you get stuck you can bring them into class next time we have a class. So here's one that looks similar to the one that we've already done. Have a shot at that. It shouldn't be too hard for you to do. Notice that we don't have an equals sign here anymore. We've got inequality. And then find the Cartesian equation of that. This is a more tricky region. Don't forget, if you've got something that satisfies two conditions, so these complex numbers have to satisfy this condition and that condition. So you've got two things going on, so you'll have to take both of those things into consideration. Have a go see how that works. That one's even trickier. So we'll talk about these when we come into class. And again, find the Cartesian equation and a last example. Okay. When you get through those questions, or if you want to try some extra questions, then try problem 15 from topic 3 in the handbook. Okay, have fun sketching curves in the complex plane.